Hi, this is Karthik. In this video, I am going to discuss about efficient mining of frequent subgraphs in the presence of isomorphism. These are the contents that we are going to discuss about efficient mining of frequent subgraphs in the presence of isomorphism in this video. Motivation, introduction, challenging problems, proposed approach, key features, basic concepts, outcomes, and the final conclusion. The main motivation was the graphs are utilizing in numerous fields, including chemoinformatics and bioinformatics. A graph provides a generic model for data representation. Frequent subgraph mining is an active research topic in the data mining community. It is difficult to mine patterns from graph databases because techniques related to graphs, including subgraph testing, typically have higher temporal complexity than their analogous operations on well-studied item sets, sequences, and trees. Due to its numerous application fields, including weblog mining, video indexing, bioinformatics, and chemoinformatics, efficient database indexing, and frequent patterns of semi-structured data, such trees and graphs mining has garnered a lot of study interest. An arbitrary graph G's support is the fraction of all graphs in set S of which G is a subgraph. Given a set S of labeled graphs, also known as a graph database, when G's support falls below a predetermined threshold, minimum support, graph G becomes frequent. The task of frequent subgraph mining involves locating every frequent subgraph within a graph database. We are going to face two difficult computational issues are at the center of every frequent subgraph mining algorithm. Finding out if a given graph is a subgraph of another graph is known as subgraph isomorphism. Secondly, an effective method to enumerate all frequent subgraphs must be found. To sort out these problems, we proposed an algorithm that we are going to see in the next slide. For the problem mentioned before, an algorithm has been introduced named as frequent subgraph mining to lower the amount of redundant candidates suggested. Makes use of a vertical search technique inside an algebraic graph framework we have created. By comparing FFSM to the state-of-the-art subgraph mining algorithm GSPAN, our empirical investigation on both synthetic and real datasets demonstrates a significant performance boost. The algorithms that are most directly relevant to our ongoing work include Ullmann's subgraph matching algorithm and Euclid association mining algorithm. Two new data structures are proposed: the DFS code trees and the unique canonical form of graphs called DFS code. Pre-ordered traversal of the DFS code tree lists all frequently connected subgraphs of a graph database using Ullmann's subgraph matching technique and a straightforward single-edge growth scheme. In accordance with the concept of the Euclid association mining method, a depth-first scheme is put out. Proposed data graphs are informed by data from sibling nodes. The key features of fast frequent subgraph mining methods are a novel graph, canonical form, and two efficient candidate proposing operations. And those operations are FFSM join operation and FFSM extension operation. An algebraic graph framework means suboptimal CAM tree to ensure that every frequent subgraph is clearly listed. Maintaining an embedding set for every frequent subgraph allows one to fully avoid subgraph isomorphism testing. Before getting into the topic, we need to know about these concepts, which are canonical adjacency matrix and exploring the CAM tree, which we are going to use in this concept. In Canonical adjacency matrix. Each adjacency matrix M in FFSM represents a graph a little different from the adjacency matrix for an unlabeled graph. Each diagonal item in M is filled with the label of the matching node, and each off diagonal entry is filled with the label of the matching edge. As we observe the figure shown above, a graph P with labels and two adjacency matrices associated with it, which shows code M1 is greater than or is equals to code M2, means code of M1 is equals to AXBXYBOYYB is greater than or is equals to code of M2 is equals to AXBOYBXYYB is what we get after applying the entire ordering. In the lower triangular component of an adjacency matrix M, any non-zero off-diagonal item is referred to as an edge entry. Every edge entry is arranged in the code based on where it belongs. Regarding M1, the first, last and second to last edge entries are in order of M21, M43 and M42. The last node of M1 is designated as M44. Submatrices A and B are derived from each other. Matrix B is derived from matrix C, and so on. Given an n cross n adjacency matrix M of a graph G with n nodes, we define the code of M denoted by code of M as a sequence of lower triangular entries of M in the order M11, M21, M22 and so on of Mn1, Mn2 and so on of Mn, n-1, Mnn, where Mij represents the entry at the ith row and jth column in the M. If we let an empty matrix be the submatrix of any matrix with size 1, we can organize the cams of all connected subgraphs of a graph G into a rooted tree as follows. Firstly, the root of the tree is an empty matrix. Secondly, each node in the tree is a distinct connected subgraph of G represented by a cam. Thirdly, for a given non-root node, its parent is the graph represented by M's submatrix. The tree obtained in this fashion is denoted as the cam tree of the graph G. For the proper understanding of this concept, we are going to take a theorem. Given a connected graph G and one of its subgraphs H, let G's cam be A and H's cam be B. Then we have code of A greater than or is equals to code of B. We define the maximal proper submatrix of an adjacency matrix M as the matrix obtained by removing the last edge entry E of M. For submatrices, we have the following two corollaries. Corollary 2.2 states that given a cam M of a connected graph G and M's submatrix N, N represents a connected subgraph of G. And corollary 2.3 states that given a connected graph G with cam M, M's submatrix N and a graph H which N represents, N is the cam of the H. Before going to explore the cam tree, we need to know about the two operations called join operation and extension operations, which are using in the cam tree. The join operation. In the join operation, the two main issues with join operation are that numerous candidates could be produced by a single join, and that a single candidate could be repeatedly proposed by multiple join operations. The simple definition to define the extension operation, which limits the nodes that a newly introduced edge can be attached to it. The extension operations main concern. Here we can see the algorithm of FFSM. Here S represents the cams of frequent nodes and P represents the cams of the frequent edges. As we observe the figures, it shows clearly the difference between the FFSM and G-span's outcome. The figure clearly represents that FFSM consistently performs better than G-span by a factor of up to 7 according to the curve. By utilizing the DTPCA and PTE datasets, we observe a comparable pattern and discover a 2 and 3-fold increase in speed respectively. Complicated datasets. Furthermore, using a variety of synthetic graph datasets, we investigated FFSM and G-span and discovered that FFSM and G-span are always competitive. And the final conclusion was by introducing two efficient subgraph enumeration operations and effectively handling the time-consuming underlying subgraph isomorphism problem, FFSM outperforms existing algorithms. Additionally, an algebraic graph framework is developed to reduce the number of redundant candidates proposed. A substantial margin of performance increase of FFSM over G-span was shown via performance evaluation utilizing multiple real datasets. Using the synthetic datasets, the effectiveness of FFSM is further validated. Here are some of the references that we have used to clearly know about the concept. Thank you.